Hello, my name is Greg Moss, and I'm going to be presenting the webinar today for ESD testing and damage prediction using XFdtd. First, I just want to start by covering a couple of housekeeping items. We do have a moderator in the webinar today, so please feel free to submit questions during the webinar, and hopefully he'll be able to answer most of the questions you have. If there are any questions that he can't handle, we will have some time for questions at the end. And of course, anything we don't get answered during the webinar, we will follow up with you shortly afterwards. Second, I am going to be showing a pre-recorded video for the demo portion of the webinar. So we've been told that during the video portion, if you've called into the webinar, you actually may not be able to hear the audio. So you really want to be using your computer audio in order to hear the demo portion of this webinar. So to start, I'm just going to give a real quick overview of the presentation. First, I'll start by giving kind of a general overview of static electricity and electrostatic discharge. Next, I will discuss electrostatic discharge testing. Then I will go over the new functionality that we have added to XF to support ESD testing. Then we'll do the demo video, and then I'll come back after the demo video for just a few quick conclusions, and then we'll have a brief Q&A session. So static electricity is something that everyone is familiar with, whether they know they are or not. We encounter it every day. There are actually multiple causes of static electricity. There's contact, pressure, temperature, and charge or electrostatic induction. The most common type of electrostatic buildup that's encountered during manufacturing is from the contact or triboelectric charge buildup. So this occurs when two materials are coming into contact with each other and actually transferring electrons, which results in a voltage difference between the two objects. And on this side here, the main takeaway that I really want you to get is just how much voltage you can have built up from triboelectric charge. Just from everyday tasks such as walking across carpet or picking up a bag, 35,000 volts. That's really kind of mind-boggling to me that you can actually have that much voltage built up from such a simple task. And you can also see another takeaway from this chart is actually how much of an effect the relative humidity of the air can have on the voltage difference between two objects. So basically, when you get this much charge build up and voltage difference between two objects, a lot of times you will end up experiencing an electrostatic discharge. Electrostatic discharge occurs when your air actually experiences dielectric breakdown and you have an ionization channel formed between the two conducting objects. So electrostatic discharge is a major issue with the electronics manufacturing industry. And at the top of this slide, you'll see I kind of have it's a quote that has been around for years, and it's somewhat unsubstantiated, but it's in the electronics industry, losses associated with ESD are estimated at between $500 million and $5 billion annually. In reality, it's extremely difficult to actually get an exact estimate of ESD cost and ESD loss. But one thing is for certain is that during the manufacturing and testing stage, it requires multiple prototypes, which can be expensive to be created and tested. If you have ESD damage occur in the hands of the consumer, then you can end up having to fulfill warranty claims, and then you also just in general lose consumer confidence. So to combat this, the electronics industry performs what is known as ESD testing. There are numerous standards which define ESD testing procedures, and in our case, on the computational side, we're a little bit more interested in the actual ESD test models or waveforms. To the right, you actually see an image of what is known as an ESD simulator or gun that is used to excite different device under tests at various locations of interest and to test them for their ESD mitigation or capabilities. So There are many ESD models defined in the various standards. Two of the most common that you typically encounter are the human body model, or the HBM model, and the CDM, or the charge device model. Like I said, there are many others. These are kind of two of the most common. The human body model has been formulated to mimic a electrostatic discharge between the human body and an electronic or conducting device. So in this case, the waveform that you're seeing here would basically mimic if you were taking your finger and going to touch your cell phone. You could have a spark discharge between your fingertip and the cell phone, and the human body model is a good representation of that. The charge device model is between two conducting objects, and where you might encounter this more so is if you're in an assembly line environment and you have a device traveling down the assembly line and it's actually picking up charge from the conveyor belt, and then it comes into contact with maybe another device or maybe a conducting wall, and you would have a discharge between those two devices. In this case, the charge device model is a good representation of that pulse discharge, ESD discharge. So ESD damage can be categorized in one of three ways commonly. And first, you have catastrophic, in which the device actually no longer functions according to design. And you may look at this picture and you may think intuitively that that is the worst type of ESD damage that could occur. During testing, catastrophic is actually the most desirable type of failure to occur. One, because you know it happened because the device will no longer function properly. And two, because there is usually very visible physical damage. It's easy to pinpoint where the failure occurred. So this can easily be pinpointed and remedied when it's still in like the design and testing stage. Latent damage, on the other hand, is the device will often still function appropriately, so you may not even know that the damage occurred, and there's usually is you can see evidence of it, but usually only under magnification. So for latent damage, there's a really good chance that this device has suffered this failure during ESD testing, but it's going to pass and it's going to end up in the consumer's hands. And over time, that damage is going to probably have subsequent discharges across that gap. And then so there's a really good chance that that's going to fail in the consumer's hands. So that's a much worse scenario. So you would have warranty claims in that case. An upset failure is what I kind of liken it to, is you may end up having the device still functions appropriately, and there's no physical evidence that any damage occurred. So you're not going to be able to determine evidence occurred. But you may have a device, maybe a semiconductor device in the device under test, which has basically been compromised by the ESD discharge. And that's going to result in unpredictable behavior once the device makes it into the customer's hands. So you may end up having, it could be things like bit error rates. Maybe your software is acting not in unexpected ways. You may be getting crashes, things like that. So again, there's no evidence of that. So that's really kind of a bad scenario. So the goals that we have for performing ESD simulation in XF is, one, we want to help engineers pinpoint locations at risk of experiencing dielectric breakdown during ESD testing. And we also want to help them pinpoint components at risk of like circuit components at risk of experiencing damage during ESD testing. And our hope is that this will allow engineers to optimize their ESD mitigation designs prior to that hardware prototyping stage. And if they have to build and test less hardware prototypes, that's going to reduce the overall product development costs and time to market. And in the long run, hopefully it will improve product reliability and consumer confidence. So this slide just shows some of the features that were added in XF to be able to support ESD testing. So the first step is importing ESD waveforms, which are defined in the ESD standards documents. A new material parameter known as dielectric strength, a new result sensor known as a dielectric breakdown sensor, and then adding rated voltage and current parameters to XF's built-in circuit components. So first is ESD waveforms from the various standards can be imported into XF using our improved user-defined waveform feature. Basically, you can take any waveform that has been generated in a text file and easily import that into XF. Some of the references, I've provided a number of references here. There's a whole body of work in the literature where people have generated analytical expressions for ESD waveforms. The ESD standards, kind of the target audience is more, you could say maybe the hardware designer or the ESD gun manufacturer. And so what you find in the standards often is the electronic circuits. They kind of describe the electronic circuits, but they do not give analytical expressions for the ESD waveforms. So there's kind of a whole body of work to determine analytical expressions for ESD waveforms, and that's kind of what we're using here. Second, we have a new material property known as dielectric strength. The dielectric strength defines the maximum electric field that a material can withstand before experiencing dielectric breakdown and losing its insulating properties. So as I said earlier, that is when you will actually have a channel. Once you have enough voltage, you will have electrons start to move. They will start ionizing other atoms or molecules, and you'll end up having an ionization channel form between two conductors, and it'll result in a discharge. So this dielectric strength is what you're defining here. If you do not want a material to be considered in your simulation for, if you do not want it to be monitored for dielectric breakdown, then you would simply check the checkbox to define it as having an infinite dielectric strength. And you're basically just saying that it's impossible for this material to experience dielectric breakdown, so it won't be considered by the detection algorithm. So second is third, I guess, the dielectric breakdown sensor. And this defines the space in your FDTD simulation that you're actually going to be monitoring for dielectric breakdown. One thing, by default, if you do not define a bounding box, the whole space will be monitored. There is some computational expense involved with actually monitoring, cell edges for dielectric breakdown. So it's actually ideal to go in and define the bounding box to your specific area of interest, and that's kind of what you see on this slide here. The other input parameter that's important on this is defining the dielectric strength for free space. So with the default value that we have here is 3 megavolts per meter, which corresponds to the dielectric strength of air at sea level. In most cases, this is what we're going to be, that's more than adequate. There may be cases where you want to change it to where you may have a different relative humidity or something like that, where you want to change that dielectric strength. Or you could be, maybe you're doing testing for a space environment where you're actually in a vacuum or something like that. And in that case, you'd want to change it to the dielectric strength of vacuum as opposed to air. And then finally, we have for all of our circuit components, we have rated voltage and rated current values, which can now be assigned. These values can easily be obtained from the component data sheets that you usually receive from the manufacturers. Similar to the dielectric strength, if you do not want the component to be monitored for over voltages or over currents during the simulation, you would simply leave it set to it having an infinite rated voltage or infinite rated current. So at this point, I'm going to start the pre-recorded project demo, and then as soon as that ends, I will come back for some conclusions, and we'll have a Q&A session. To demonstrate ESD testing simulation in XF, we have imported a multi-layer PCB and created a simplified ESD probe, which will be used to excite the PCB with ESD waveforms at various locations of interest. The use of a simplified ESD probe is acceptable in this case because we are much more concerned with the electromagnetic fields and the currents generated on the PCB than we are with, say, the electromagnetic fields generated on the surface or the interior of an actual ESD simulator or gun. Once the geometry has been defined, material definitions need to be created and assigned to the geometric objects. To save time, this has already been done for this project. You can see here that the pads, surfaces, nets, and drills have all been assigned perfect electric conductor definitions. and this means that they will not be examined for dielectric breakdown during the simulation. On the other hand, the substrate has been given properties of FR4, and in this case, the dielectric strength of FR4 is approximately 20 megavolts per meter, which has been entered here. For materials that you do not wish to be examined by the dielectric breakdown algorithm, you would set them to have infinite dielectric strength by checking this checkbox. And that will mean that they will be ignored by the detection algorithm, and that it's essentially impossible for them to experience dielectric breakdown during a simulation. After completing the material assignments, the next key aspect of ESD testing simulation is to define the ESD waveform. To do this, XF's user-defined waveform feature is utilized. Here we have imported a 15 kilovolt HBM waveform from the paper of Keenan and Rosie in 1991. You can see here that it has a peak amplitude of about 75 amps and is approximately 100 nanoseconds long. This waveform, the characteristics of this waveform actually are very important for setting up other aspects of our simulation, so we will refer back to it several times. Now that the ESD waveform has been defined, we can create the ESD feed. First, to do this, we'll create a new circuit component definition called the ESD current source. We want this to be what we call a hard current source, which basically means that there's no source resistance. And we want the amplitude to remain at 1 because the amplitude of the ESD waveform is already defined by the waveform definition. So here you can see that this is where we have assigned the 15 kilovolt HBM waveform to this current source. Now that we have the ESD current source circuit component definition, we can now define the circuit component feed, which will be placed between the tip of the probe and the location where we want to excite the PCB. Here I've already created this feed and it's simply set to invisible, so I'm going to set it as visible. And you can see here that it's been connected to the tip and then to this trace pad on the PCB here. And then here in the properties of the circuit component feed is where you actually assign the component definition to the ESD current source. In addition to the ESD feed, you can see that I also have a number of passive components defined, and this is to demonstrate XF's new rated component capability. So first I will go into the 50 ohm resistor and I will assign it with a rated voltage of 30 volts. I will assign the inductor with a rated current of 0.44 amps, and I will assign the capacitor with a rated voltage of 16 volts. All of these rated component values can easily be found on the component data sheets that are provided by the manufacturers. For any component that you leave with an infinite rated voltage or infinite rated current, they will not be monitored during the simulation for over voltages or over currents. So here I have the actual circuit components all set to invisible, so now I will make those visible. Let me zoom out and then I can show I basically just placed these components at the end of these traces. And this is not necessarily a real design. This is I've just placed these components here to demonstrate the new rated voltage feature, rated current feature. Now that we have the materials, waveform, and circuit components set up, we need to define result sensors to obtain our desired ESD results. First, we'll define a planar E-field sensor to obtain electric fields on the surface of the PCB. Here, the surface data definition, the surface sensor definition has already been defined ahead of time. This is collecting transient E-fields with an end time of 20 nanoseconds and then a sampling interval of 500 times the time step. And then once we have the definition defined, then we can come into the near field sensor and create a new planar sensor. We want this to be with a normal in the Z direction, and then we can actually place it on the surface of the PCB. So lock that to the center and then there. And then here you can see that the surface sensor definition has already been defined, associated with the near field sensor. So while the transient E fields on the surface of the PCB, they provide a very interesting insight into how the fields are propagating and the currents are propagating on the surface of the PCB, but that they do not necessarily give us insight into locations of where a dielectric breakdown is likely to occur. So to obtain that result, you actually we have a new near field sensor called the dielectric breakdown sensor. Here, we already have one defined. And the properties of this sensor, this is very important to set your free space dielectric strength. So basically, this defines the dielectric strength for everywhere in the simulation where you have free space material. In this case, the default is 3 megavolts per meter, which is the dielectric strength of air at sea level. This value, while in most cases that value is going to be sufficient, there may be special circumstances where you want to consider the relative humidity of air, and maybe you will need to change the dielectric strength in that case. Or maybe you're doing testing for, say, a space environment, and in that case you would actually want to enter the dielectric strength of a vacuum instead of air. Also, then you can define the bounding box of the dielectric breakdown sensor, and this is also very important because you want to achieve as much computational savings as you have. Monitoring the whole simulation space for dielectric breakdown can be a little computationally expensive. So generally, I usually start by I set the bounding box of the sensor to that of the geometry, and then I come in and fine-tune it a little bit more specifically to the area I'm interested in. So in this case, I'm not interested in dielectric breakdown around the ESD probe, so I'm going to zoom this in closer to the multi-layer PCB, come down a little bit closer here. I can change my view, and really I'm just going to kind of make this as tight to my area of interest as I can to get as much computational savings as possible. At this point, we have our project pretty well defined, but we still need to set up our XFdtd simulation settings. First, to do this, we want our PCB and we want our probe to be grounded. So we're going to actually edit our outer boundary conditions, and we want to set the -z boundary to be PEC. Now we need to define our XFdtd grid. Defining the XFdtd grid for a ESD simulation is somewhat different than defining a grid for many of XF's common applications. The first thing we want to consider is the frequency range of interest. Since this is an electrostatic discharge, you're obviously interested in a phenomenon that's occurring in the static limit. And you can see that really you're defining your frequency range of interest by the ESD pulse that you're inputting into the system. And in this case, you can see that there's really no high frequency content in the waveform. So all of the frequency content is very down approaching DC. So we're not, what that means is the XFdtd grid is not going to be defined or limited based on the frequency range of interest. It's more the much more important aspect of the project in finding the grid is making sure that you adequately represent all of the geometric detail of the device under test. So now I'm going to come into the XFdtd grid settings. And since we are not using a frequency range of interest in this case, our ProGrid optimized gridding algorithm actually uses the frequency range of interest to help with its automatic meshing. So that's not really going to be of use to us here. So we're going to go ahead and we're going to turn that off. And we're just going to start by using 1 millimeter target grid cells. And then another thing we want to do is we want to come over to the extents. And if you recall, I said that we want the PCB and the probe to both be grounded, and we have a PEC outer boundary condition in the -E direction. So we want to go ahead and we want to set that to 0, and that will actually, the probe and the PCB will be laying flat on that -E ground plane. And again, in an effort to get as much computational savings as possible, we don't need to have 20 cells of padding in all these directions. So we can really lower this down safely to probably about 5 cells of padding in all of these directions. And so at that point, we can go ahead and we can apply this, and you can see only using 71 megabytes of memory. So that's a really coarse mesh. if we pop over to the mesh view, then I think what we're going to see is that this is not, so just with the, kind of 1 millimeter default cells, we're not going to be accurately representing the PCB, but by a long shot. So here what we've done is I've come over and I've actually used a local grid region defined on the PCB itself. And you can see that we're going much coarser or much finer here, 0.1 millimeter X and Y direction, 0.2 in the Z direction. Then going ahead and applying that, we can see that this gives us a much more reasonable mesh for the PCB device. Let me get up to the top layer here, top traces. And then if you kind of zoom in on the mesh in this case, you can see that, all your traces are getting, adequately represented in the FDTD mesh. So that's kind of the key to setting up a mesh for these ESD testing simulations, is you're not necessarily working with a frequency range of interest. So the goal is really to have the cells as large as possible while maintaining, correct geometric detail of your device under test. And one of the real challenges with these ESD simulations is that because of the fine detail in the geometries, and you have to use small FDTD cell sizes, which results in a small FDTD time step. And when you come back and you look at the source waveform, these waveforms relative to the FDTD time step are actually very long. And that's why it's really important to try to kind of squeeze out every little bit of computational savings that you can from when you're setting up these simulations. So now we have everything defined and we're really ready to create our FDTD simulation. So we'll come over here, we'll go to create FDTD simulation, ESD test, and like I said previously, these are a little bit different than our standard XF applications. So we're not doing, you could conceivably have a parameter sweep for one of these, maybe where you are changing the location of where you're exciting the device under test with the ESD pulse. But for this simple test problem, we're not going to be performing any parameter sweeps. We're not interested in S parameters. We're not collecting any steady state data. So really the only thing that you really have to focus on is specifying the correct termination criteria. So to do this, again, you want to refer back to your ESD source waveform. And from experience, typically dielectric breakdown, or the rated voltages and currents being exceeded in the circuit components, it generally happens around the peak, around the peak of this ESD waveform pulse. So the first option you could have is you could just say, okay, I want to actually allow the entire pulse to play out for my FDTD simulation. So in that case, you would set your termination criteria to just match the length of the pulse. So in this case, that would be 100 nanoseconds. As I said previously, in an effort to kind of squeeze out as much computational savings as possible, since most of the failures occur around the peak of the pulse, you can come down and you could say maybe cut it in half, simulate it out to 50 nanoseconds. For this test problem, I'm actually coming in even a little bit farther, and I'm going to simulate it to about 20 nanoseconds. That's going to give this peak pulse plenty of time to kind of propagate through the device and show us points of at risk of dielectric breakdown and overvoltages and overcurrents. So after examining the waveform, you can see here that I've come in and I basically I'm setting my termination criteria at the simulation time of 20 nanoseconds. We're not interested, so for these ESD simulations, we're not interested in detecting convergence. It really all comes down to giving adequate time for that ESD pulse waveform to propagate through the space, and that's how we arrive at our maximum simulation time. So now that we have that set, we can go ahead and we can create our simulation. So now in order to save some time, I'm going to jump over to results from a previous run. Let's zoom back out to capture the whole geometry. So we'll start by, we save the transient electric fields on the surface of the device with the planar sensor. So we'll start by taking a look at that. Click over here to sequence, and then we'll just go ahead and play that. it'll take just a moment for it to compute the bounds of the result bar. So here you can see the pulse actually propagating from the pad down the trace and then to this part of the PCB. So like I said previously, this makes for kind of a very neat, movie. It's neat to see how the fields propagate. Some interesting things you can see that you're actually getting some pretty high fields over in different parts of the PCB where, maybe you wouldn't necessarily anticipate that beforehand. So it does give some interesting insights, but just looking at this field movie, it really doesn't tell us like, exact locations of where we should be concerned about dielectric breakdown occurring. So I'm going to go ahead and stop this, unload that result. Now I'm going to pull up the new dielectric breakdown sensor result, and this actually makes it much easier for an engineer to pinpoint locations at risk of dielectric breakdown. The first thing I usually do is, since this is highlighting specific FDTD cell edges, I usually come in and I change my size factor to about 5 or so, and that makes it a little bit easier to, from a distance, see locations that have been highlighted. Now, what this is presenting, it's actually a time domain result. So at this first sequence, each moment in time during the simulation that a cell edge either experiences dielectric breakdown for the first time, or if it actually has a higher dielectric breakdown than it did in any previous time step, then the result gets saved at that time step. So what we're seeing here is actually the first moment in time that a FDTD cell edge exceeded its dielectric strength. And so we can actually go and we can just zoom to the max field edge, and this kind of takes us in and shows us the first cell edge that exceeded its dielectric strength. And in this case, you can see this is a Z-directed cell edge, so that's actually a free space. That's an air cell edge that exceeded the 3 megavolts per meter. So there are a couple of things of interest. The first cell edge, seeing the first location that exceeded the dielectric strength is of interest. And then, a lot of times it's actually pretty useful just to go ahead and just go to the last sequence. And then in this case, this gives you kind of a total history of all the edges that exceeded their dielectric strength and by how much. The value that's being displayed here is actually the dielectric breakdown ratio. So this is the multiple of how far the dielectric strength was exceeded, by how much the dielectric strength was exceeded. So, in zooming in and looking at this, it's actually interesting. You see that you have a lot of the Z-directed edges, which again, those are all air edges being exceeded. And really what that would kind of represent in this case is, since that's air and since that's kind of going above the trace, really that may be what you would see in a real ESD test, is you might actually have a little bit of a corona breakdown that's happening above your trace. For our case here, we're really kind of more interested in getting, potential locations maybe between the traces on the PCB that break down. So instead of showing all of the every direction of the edges, we can actually choose to either show the X, Y, or Z. So maybe if we click on the X, hit apply, this result kind of is a little bit more informative to me. So you can actually see that you have a pretty high risk of actually having a dielectric breakdown between these two traces, and you have a high risk of a breakdown coming between, when you're actually making this turn. And you can actually go all the way down to the end, and you can see that you have some far away from where you're actually exciting the PCB with the probe. You actually see that you have some areas of high risk way down here, and same thing with the Y direction. So you see that, again, when you're making that, you're changing direction and your trace is right there, and it actually results in an increased chance of dielectric breakdown. So, these results, this really would help an engineer at a glance determine locations where they may need to actually come back and revisit their ESD design. Maybe these traces should be moved a little bit farther apart. Maybe there needs to be, a little bit of shielding, or maybe a different material used in that area. So, this new dielectric breakdown sensor, we hope, really helps engineers at a glance determine locations at risk of ESD breakdown, and will let them optimize that maybe before actually developing their hardware prototypes. And finally, I'm going to pull up the rated component results from the voltages and rated currents that we defined earlier. And again, this gives a real quick summary of all of the components in your simulation that actually exceeded their rated value during the simulation. So this is a useful result for both ESD testing or even just some of the standard RF simulations that you may be doing in XF. Gives the engineer a real quick summary of components that are at risk of experiencing permanent damage. So they may need to go in and maybe get a more expensive component with a higher rated value, or they need to go in and actually maybe redo some more of their layout design. So with that, that concludes this demo of our new ESD testing features. I hope it was informative. Okay, I hope that got everyone excited to run off to their computers and do some ESD simulations. So just kind of, again, a couple of conclusions that I want to state to conclude things here is first and foremost, ESD simulation does not replace ESD hardware testing. That's still a step in everyone's manufacturing procedure that are going to have to do. Really, again, what we're trying to do here is give the engineers, from talking with industry, there might be a little bit of black magic involved with this ESD testing, where it's like you zap your device in several different places, but then it's kind of like then you have to go on a little bit of a needle in a haystack sometimes hunt to try to determine where the failures occurred. So again, we're trying to let engineers optimize their ESD designs prior to hardware prototyping. And then, number two would be to maybe help them determine locations that fail during their actual hardware testing if they can't visually determine where that failure occurred. And one thing I do want to stress is that what we're doing here is we're not necessarily the results that we're giving. They're not guaranteeing that you're going to experience ESD failure in a certain location. They're showing you the risk, so it's more of not a guarantee, but it is easily you can quickly see areas at risk, which to me is very valuable and would let an engineer optimize their design well with that information. And hopefully this is only the beginning of this feature for us. There are some plans, and there is some research that's been done into actually introducing more multi-physics aspects of ESD analysis. One thing that could be done is, or that we'd like to do, is actually model the spark discharge, transient spark discharge. So when a cell has exceeded its dielectric strength, then actually simulate the spark discharge, and that result can be coupled back into the FDTD simulation. There are plenty of ways to model. There are plenty of models that have been developed to simulate spark discharge, transient spark discharges. And then another potential multi-physics aspect would be the thermal damage. You could actually have a thermal simulation going on, calculate the heat resulting from a ESD discharge, and maybe predict the damage to the materials in the surrounding area. So those are kind of my conclusions for the webinar. So now here are some references. A lot of these references are for the waveforms that I kind of showed earlier. And then we have some time for some questions. And looking over at the questions panel, there's not a lot of action going on over there. So I have a couple of questions that I've received about these features already. I can answer some of those if maybe those are common questions that people will have. One question we've received is about actually having a library of ESD waveforms. And currently, like I said, there's kind of a whole area of research to develop to come up with the analytical models for those waveforms. And Yes, I would like to have, I am hoping that, we will be able to incorporate actually a pre-built library of ESD waveforms. For the time being, you do have to use you have to generate the waveform outside of XF and then import it using the user-defined waveform function or feature. So, that's one question that I've received. There was another question that is slipping. Oh yes, another question that I received was it involved whether we could actually incorporate say circuit simulations into our XFdtd simulation in conjunction with this feature. And that is another one that currently you can import like SPICE netlist files, so arbitrarily linear netlist files, arbitrarily complex, into your XFdtd simulations. You can define rated voltage and current for what you would say the parent netlist component. So that would monitor the voltage and current, say, going into and out on the cell edge where the complex circuit is actually connected. We do not support rated voltage and currents of, say, children elements within those net lists presently, but again, that is a feature that would be somewhat not too challenging to add. And if there is enough customer interest in those types of features, that those are definitely things that can be added. And so that, if no one has any other questions, which I'm not really seeing any pop up at the moment, then here is contact information. Any additional questions that you may have, certainly send them in, and we can do our best to get them answered. I hope you enjoyed it. Thanks to everyone for attending.